Welcome to our presentation on MIDAS regression. The guiding principle for this module is, don't waste data. Use every observation. This powerful statement encapsulates the core idea behind today's topic. We will delve into how to bridge the frequency gap that often exists in economic data, moving from the foundational theory to practical forecasting applications using EViews. For instance, imagine needing to predict next quarter's economic growth, but the most relevant and timely data you have is monthly stock market returns. That's precisely the kind of challenge MIDAS regression is designed to address. So, what exactly is this frequency gap, and why is it such a common dilemma in economic metrics? In many real-world scenarios, we face what's called the frequency mismatch dilemma. Our objective might be to forecast a low-frequency variable, such as quarterly gross domestic product, but the freshest and most informative data we have available is often high-frequency, like monthly employment statistics. The core problem is that standard regression models, which are foundational in econometrics, rigidly demand that all variables, both dependent and independent, exist on the exact same timeline. The traditional workaround for this has been to aggregate the high-frequency data, for instance, averaging 3 months of employment figures to align with a single quarter of GDP. However, this seemingly simple solution comes with a significant and often overlooked cost. By aggregating, we inevitably throw away valuable intra-period signals, destroying crucial timing information and the true volatility inherent in the higher frequency data. This loss can significantly impair our forecasting accuracy. Fortunately, MIDAS regression offers a powerful solution, elegantly removing this restrictive requirement and allowing us to leverage all available data efficiently. This decision tree guides us through selecting the appropriate MIDAS model for our specific data and research goals. The initial step, as always, is confirming that your variables indeed operate at different frequencies. If so, we then consider the lag length and the primary focus of our analysis. If the lag length is relatively small, for example, transitioning from monthly to quarterly data, MIDAS, or unrestricted MIDAS, is often suitable, as it estimates individual coefficients for each lag. However, if you're dealing with a wide frequency gap, such as daily to quarterly data, the number of lags becomes too extensive for MIDAS. In these cases, restricted MIDAS is essential. It employs a weighting function, like beta or Almon, to efficiently summarize the impact of many lags with just a few parameters, thereby saving precious degrees of freedom. Within restricted MIDAS, you'll choose between a flexible shape, typically beta or Almon weighting, or a simpler step weighting. Lastly, if your primary interest lies in modeling variance or volatility, then the specialized MIDAS Gauge model is the most appropriate choice. Remember, the general rule of thumb, and the EViews default, is to use restricted MIDAS with beta Almon weighting when you have a wide frequency gap, precisely to optimize your degrees of freedom and ensure model stability. We've discussed why restricted MIDAS models are necessary for long lag structures to save degrees of freedom. This slide lays out the primary weighting methods available within that framework. Step weighting is the most straightforward approach. It groups lags and assigns the same weight to each lag within a group, making it a simple approximation useful for initial rough estimates. Next, Almon weighting, also known as a polynomial distributed lag, uses a polynomial function to create a smooth weighting curve. It offers flexibility, but one must be mindful of potential instability at the beginning and end of the lag window. Then there's MIDAS, or unrestricted MIDAS. While it imposes no shape restrictions and estimates each lag's weight individually, it is best suited for shorter lag structures, typically when moving from monthly to quarterly data, where the number of parameters remains manageable. The gold standard in the literature, especially for longer lag scenarios, is beta weighting. Its strength lies in its remarkable parsimony. It uses just 2 parameters, θ1 and θ2, to define a wide variety of flexible and stable weighting curves, regardless of how many lags you're including. This efficiency prevents the model from becoming overly complex and unstable, making it the default and often preferred choice in applications like EViews. This ability to capture complex patterns with minimal parameters is why beta weighting is so powerful. Let's now delve deeper into the diverse shapes these two beta parameters can create. This slide presents the core mathematical formulation of a MIDAS regression model. On the left, YT represents our low-frequency dependent variable, such as quarterly GDP growth. On the right, XTM, with its superscript M, is our high-frequency regressor, which could be monthly employment figures or stock market data. The innovative part lies in the middle, B of L to the 1 over M. This is the weighting function, acting as a crucial bridge between the different data frequencies. Instead of individually estimating a coefficient for every single high-frequency lag, MIDAS efficiently estimates a few hyperparameters, denoted by theta, that collectively define the entire shape of this weighting curve. Essentially, we're running a regression where the coefficient beta 1 isn't a static number, but rather a dynamic curve. This curve dictates how the influence of past high-frequency observations is distributed, allowing us to capture nuanced temporal relationships without losing valuable information. By estimating the two theta parameters, the beta function can produce various economically intuitive shapes. A common one is the decaying weights pattern. This implies that the most recent news matters most, and the influence of past data gradually fades. It can also form a hump-shaped curve, useful when a shock's impact is not immediate but delayed, peaking after a few periods. A U-shaped pattern can also be captured, relevant for modeling cyclical or seasonal effects, where period beginnings and ends are more important. EViews estimates these shape parameters, theta, not every individual lag coefficient. In practice, to ensure model stability and economic sense, we often impose constraints, such as setting theta 1 to 1 to force a decaying pattern, or restricting the weight at the final lag to be 0. Before we can start estimating these models, there are a few important assumptions and data conditions we must satisfy. First, as with most time series models, the variables must be stationary. You'll likely need to use transformations, like logs or differences, for example, d log GDP. Second, you must select a fixed lag window. This means deciding how many high-frequency periods you want to include in the model, for example, 12 months of data. Third, the high-frequency data must be regularly spaced. MIDAS cannot handle irregularly timed data. Crucially, you must ensure there are no gaps, like missing trading days, as these missing values will propagate and shrink your estimation sample. Finally, for EViews specifically, you need a multi-page workfile. This means your low-frequency and high-frequency data must reside on separate pages within the same workfile. If you are using daily financial data to predict quarterly earnings, you must ensure your daily data series has no missing values for weekends or holidays. You would need to fill these gaps or use a workfile structured specifically for 5-day weeks. With these conditions met, let's walk through a practical case study of forecasting GDP in EViews. To begin estimating a MIDAS regression in EViews, you'll first need to navigate to the equation estimation window. The most common path is through the EViews menu bar by selecting Quick and then choosing Estimate Equation. Once the Equation Estimation dialog box appears, you will see a Method dropdown. Here, you'll select MIDAS from the available options. A helpful shortcut is that you can simply type MIDAS directly into the method field, and EViews will instantly switch to the correct mode for you. EViews is designed to handle much of the underlying data management automatically, taking care of the plumbing like page linking and frequency conversion between your low and high-frequency data pages. For those who prefer command line execution, the alternative is to use a command like equation eq1.midas to create a new MIDAS equation object. This step sets the stage for defining your dependent and high-frequency variables, which we discussed earlier, ensuring EViews is ready to bridge those frequency gaps effectively. Here we see the EViews equation estimation window, where we set up our MIDAS model. Our dependent variable, d log real GDP, ensures stationarity, and we include standard low-frequency regressors, like a constant, c, and a lagged GDP term, d log real GDP -1. The crucial part for MIDAS is specifying the high-frequency regressor. As highlighted, we must use the page name, series name syntax, as shown with monthly emp. This explicit naming convention tells EViews precisely which workfile page contains the high-frequency source data and which specific series within that page to use. This page name, series name format is not merely a suggestion, it's a mandatory requirement for EViews to correctly link the data and bridge the frequency gap for model estimation. Our goal in this case study is to forecast quarterly U.S. real GDP using monthly non-farm payrolls, which is a crucial measure of employment. This setup is a classic example of a nowcasting problem, where we aim to predict current or very near-term economic activity. To implement this in EViews, we structure our data in a multi-page workfile. The first page, quarterly page, holds our low-frequency real GDP data from 1947 to 2011. The second page, monthly page, contains the high-frequency non-farm payrolls data, spanning from 1939 to 2011. The core logic behind this approach is incredibly powerful for real-time analysis. Since employment numbers are released monthly, we gain the ability to update our quarterly GDP forecast up to 3 times before the quarter officially ends and the actual GDP figures are published. This real-time monitoring capability is precisely what we refer to as nowcasting. Our approach is based on the work by Armesto, Engenman, and Owayang from 2010. Let's now explore how to specify this model within the EViews estimation dialog. We begin our MIDAS regression in EViews with model specification. Our dependent variable is dlog real GDP, transformed to ensure stationarity, which is a crucial assumption for most time series models. For the low-frequency regressors, we include a constant, c, and an autoregressive term, dlog real GDP -1, to account for persistence in GDP growth. The key component, however, is the high-frequency regressor, monthly page/dlog m. This specific syntax, page name/series name, is essential. It instructs EViews to correctly link the dlog m series from our monthly page workfile to the current quarterly page estimation. It is important to note that ARMA terms like AR1 are not permitted in MIDAS estimation. Instead, you must use explicit lags such as y-1. After correctly specifying these variables, we're ready to define the weighting scheme and lag length for our model. Moving on to step 2. We configure the core settings for our MIDAS regression model in EViews, the lags and weights. First, under MIDAS weights, we select beta, which is the most widely used and flexible option due to its ability to generate diverse, stable weighting shapes with just 2 parameters. Next, we define the lag length. For a monthly to quarterly model, a range of 3 to 12 lags is generally considered common practice. In our case, we've set the lags to 9, meaning the model will consider the past 9 months of employment data to predict the current quarter's GDP. Finally, under constraints, you'll see endpoint equals restricted. This is a useful practice, especially if the generated weight graph appears chaotic. Restricting the endpoint to 0 forces the influence of very old data to completely diminish, contributing to a more stable and economically sensible model. With these crucial parameters set, we're ready to run the estimation and examine the results. After running our MIDAS model, this is the output we receive. We have 2 main sections of coefficients. First, we see the coefficient for our low-frequency autoregressive term, dlog of real GDP -1, which is 0.35 and significant, indicating persistence in GDP growth. The crucial part is under MIDAS coefficients. The slope for employment, EMP, is 1.91 and highly significant with a p-value of 0.000. This confirms that employment indeed has a strong and statistically significant predictive power for GDP growth. Below this, we find theta1 at 1.00 and theta2 at 5.43. These 2 parameters are fundamental because they define the precise shape of how the past 9 months of high-frequency employment data influence our quarterly GDP forecast. Lastly, an R-squared of 0.45 indicates that our model explains 45% of the variation in GDP growth, which is a good fit. These theta values, while just numbers here, actually paint a picture of how the influence of employment data is distributed over time, which we'll visualize next. A crucial diagnostic step after MIDAS estimation is to visualize the calculated weights. The weighting curve shows a clear downward trend, indicating that the most recent employment data, specifically lags 0 and 1, carry the highest predictive power for GDP. Conversely, the influence of older data, such as lags 8 and 9, smoothly diminishes towards 0. This decaying pattern is highly intuitive and makes strong economic sense, as more current information is generally more relevant for forecasting. This visualization also serves as a vital sanity check for our model. A smooth, well-behaved decay confirms the model's stability. Conversely, if these weights were to explode or oscillate wildly, it would alert us to potential problems, like an overly long lag length or issues with data stationarity. With a validated and sensible model, we can now proceed to the exciting step of forecasting.
We've reached the final and most exciting step of our MIDAS model, forecasting, and specifically what we call nowcasting. Nowcasting isn't about predicting the distant future, it's about predicting the present or the very near future for a period that has already begun, but for which official data is not yet available. The graph visually demonstrates this. We have actual GDP growth up to February, and then our model provides a forecast extending into the future months, with the immediate portion being our nowcast. In our ongoing case study, this means we can leverage available monthly data, such as January and February's employment figures, to generate a robust estimate for the entire first quarter's GDP, long before the official Q1 numbers are released. This real-time capability is invaluable. Central banks, for example, heavily rely on such nowcasting models to continuously monitor the economic pulse, enabling them to make timely policy adjustments proactively, rather than reacting to outdated information. For those who prefer working with command line in EViews, this slide provides a quick cheat sheet for MIDAS estimation. The general command structure starts with equation, followed by a name for your equation, then MIDAS with various options and parentheses. After that, you list your dependent variable and any low-frequency regressors. Finally, you specify your high-frequency regressors using the mandatory @page series syntax, as shown with monthly.dlog.emp. Inside the MIDAS options, you can define the lag type as fixed, set the lag's length, for example, lags equals 12 for 12 periods, and specify the weighting scheme, like MIDAS weighting equals beta for beta weighting. When troubleshooting, remember to check for missing values in your high-frequency data, ensure all variables are stationary, and crucially, verify that your data pages are correctly linked within the EViews workfile. To conclude, MIDAS regression stands as a powerful tool that allows us to effectively manage the complexities of mixed-frequency data. It enables us to sift through the noise of high-frequency observations and extract meaningful signals for predicting low-frequency trends, all without the pitfalls of manual aggregation. By leveraging techniques like beta weighting, MIDAS provides an efficient and robust framework for understanding how rapidly changing indicators influence slower-moving economic variables. This capability is